Hi everybody, in this video we will talk about 3 more reactions in addition to a concept known as net ionic equations. So let's first talk about single displacement reactions. In a single displacement reaction, the 2 elements in the front switch places. So as you can see, the Zn and the silver switched places and now they become this. So note that silver nitrate and zinc nitrate are salts, and if they are salts, they have to have balanced charges that add up to 0. So that's why you see 2 nitrates here and 1 nitrate here, since this is +1 and -1, and this is +2 and -1 times 2, which is just -2. So be sure to balance out the charges on the salts when you write single displacement reactions. Now, something else you should notice is that this is zinc, and this is silver plus, and this is zinc 2 plus, and this is silver. So something else you might notice in single displacement reactions is that the first solid metal will become a cation, and the first cation will become a solid metal. So essentially they're switching places because the zinc solid went from a solid to a cation, and the silver cation became silver metal. So let's now talk about what net ionic equations are, since they are essential to understanding how single displacement reactions work. A net ionic equation is a reaction that excludes the spectator ions, and I'll show you what they are, but a spectator ion is an ion that does not react nor change. So let me write aqueous there to be sure. So in order to write net ionic equations, we have to first know something. We have to know that when a salt such as silver nitrate enters solution and is aqueous, it is technically separated and dissociated, because in the video about electrolytes, we talked about how if a salt dissolves, it will dissociate completely. So we can rewrite that reaction as zinc solid plus silver plus aqueous plus NO3 minus aqueous. So notice how I separated the salt in its aqueous form into its separate components, because this is what is actually happening in the water. In the water, the silver cations and the nitrate anions are actually separated. So let's write the product. So it would be silver solid plus zinc 2 plus aqueous plus 2NO3 minus aqueous. So notice how the zinc nitrate separated into the zinc cation and the nitrate anions. So how about this? Let's balance the reaction first before we move forward. So in order to balance the top reaction, we will have to probably add a 2 here to balance out the nitrates. And since we have 2 silvers on the left side, we have to have 2 silvers on the right side. And now on the left-hand side, we have 1 zinc, 2 silvers, and 2 nitrates. And on the right side, we also have 2 silvers, 1 zinc, and 2 nitrates. So our reactions balance, and now let's balance the bottom part. So if it's 2 AgNO3, then it's going to be 2 Ag and 2 NO3. And if there's 2 silver, then there's 2 silver. So now let's figure out what the spectator ion is. The spectator ion is the ion that does not react or change. So in this reaction, what is not changing? Well, it seems like the nitrate is just staying, nitrate in its aqueous form. And look, it's not changing at all. So therefore, nitrate is our spectator ion, and we exclude the spectator ion in our net ionic equation. So let me erase the 2 nitrate ions. So I rewrote the reaction here in its net ionic equation form, and notice how nitrate is not there. So in this, you can clearly see that the zinc is losing electrons because it's becoming more positive, and the silver is gaining electrons and, becoming less positive and returning to a neutral state. So this is the nature of single displacement reactions. So now let's look at our second type of reaction, a double displacement reaction. A double displacement reaction happens when the front two elements switch places. So it's the same as this, the front two elements switch places, but instead of having, one and two things, you actually have two and two things combined together. So let's see how it differs. So the front two elements switch places, and none, one, or both of these products precipitate or turn into solid. So let me put the states here. This is aqueous, this is aqueous, this is a solid, and this is aqueous. So notice how the lead 4 chloride is our precipitate because it's the thing that turned into solid after the reaction happened. So for these reasons, double displacement reactions are also called precipitation reactions. So can we write the net ionic equation for this? Well, of course. Let's try that. So we have to separate all of these into their individual, ions, and let's actually balance it first. So we see 4 nitrates here and 2 nitrates here, so I'm inclined to put, 2 here. And if we put 2 there, then we have to put 2 here to balance out the calciums. And now on both sides, we have 1 lead, 4 nitrates, 2 calciums, and 4 chlorides. So I think this is balanced. And now let's write our net ionic equation. So we will write Pb4 plus aqueous, and 4 nitrates, aqueous as well, and 2 calcium cations, aqueous, and 4 chloride anions, aqueous, all coming to form PbCl4 solid. Now, why did I not separate it? Well, I only separate salts when they are in their aqueous form, meaning they are dissolved. So once they are dissolved, they will automatically dissociate into 2 ions. But in our case for lead 4 chloride, this is a solid and it hasn't gone into solution or dissolved yet. So it stays, PbCl4 and does not separate since it technically hasn't dissolved in water. So you might have seen this, but if you put too much salt in water, the salt will stop dissolving, and the salt that stays solid will not dissolve and separate into its cations and anions. So in this case, the lead 4 chloride will stay lead 4 chloride because it did not dissolve into the solution, most likely because it was insoluble and not a lot of it could dissolve. So we'll keep it as lead 4 chloride. And now let's do the second part. So it's going to be 2 calcium aqueous and 4 nitrates aqueous. So I forgot the charge, so let me put the charges. And there you go. We have the full, reaction. And now let's get rid of spectator ions. So I see that the nitrates are not changing, so they are spectator ions. And I see that our calciums are also just spectating and they're not reacting. So they are also spectator ions. But our lead and our chlorine are combining to form a solid. And you see clearly that these 2 aqueous forms are turning into a solid form. And that's technically changing. So those are not spectator ions because they are changing themselves into a solid. So let me rewrite this reaction to get rid of the spectator ions. So I rewrote the reaction without the spectator ions, and as you can see, lead 4 cation plus 4 chloride anions combine to form a lead 4 chloride precipitate or solid. So this is known as a precipitation reaction. And notice how 2 ions combine to form a salt, and that is the essence of a double displacement reaction. So now let's look at our last type of reaction. A neutralization reaction occurs when an acid and a base combine. So when we've talked about acids and bases, such as in the video about naming acids and the video about electrolytes, I talked about how there were strong acids and weak acids. So there are 4 combinations in which these can combine. So we can have a strong acid, strong base combination, strong acid, weak base combination, weak acid, strong base combination, and a weak acid, weak base combination. And we will go over all 4 of them in this video using things that we have already seen, because in the future there will be more videos about neutralization reactions and they will be a little bit more complex, but for now I am just doing the very basic ones, the ones that I guess you should recognize. For example, you should recognize that ammonia is a weak base, and this should be the only weak base that you should know for now. We will introduce more weak bases later, but ammonia should be one of those weak bases that should be in your list right now. So let me erase this, and now let's go over the 4 types of acid-base reactions. So the first reaction we will look at is between a strong acid and a strong base. So a strong acid such as hydrochloric acid and a strong base such as sodium hydroxide will react to form water and a salt. So now let's write the net ionic reactions. So HCl completely ionizes in water, so it will be H plus and Cl minus, because remember, strong acids and strong bases ionize completely in water, and in this case our sodium hydroxide is dissociating, but other strong bases will ionize, as you will see later in the future. So sodium hydroxide will dissociate into sodium plus and hydroxide, and the only reason why it's dissociating is because sodium hydroxide, although a strong base, is also a salt, so that's why it dissociates, and it forms water in its liquid form, and sodium plus aqueous and chloride aqueous. So let's find the spectator ions. So sodium appears on both sides unchanged, and chloride appears on both sides unchanged as well. So our net ionic reaction for strong acids and strong bases is the following. So the net ionic reaction for a strong base and a strong acid will typically be H plus OH minus becomes H2O liquid. So in net ionic equations, we exclude the spectator ions. But does that necessarily mean that the spectator ions are not there? Well, that's not true. The spectator ions are there. So around this reaction, there might be sodiums and, chlorides floating around, but they're not actually reacting because I guess they're just spectating the reaction and they're not a part of it. So although they're not a part of the reaction, they still exist in the solution, since hydrochloric acid and sodium hydroxide contain chloride and sodium, so they will still be there, but they will not take part in the reaction. So I forgot to mention one more thing, but in neutralization reactions, an H plus is transferred from the acid to the base. Now this is a very basic definition, but it will do for now until you get into future videos where we really talk about what acids and bases are. But for now, just know that in a neutralization reaction, an H plus is transferred from the acid to the base. So in this case, the H plus in hydrochloric acid transferred, I guess, its H plus to the OH minus in sodium hydroxide, and they kind of combine together to form water. Now, knowing that, let's look at another example of a neutralization reaction between a strong acid and a weak base. So let's take a strong acid such as hydroiodic acid, and let's mix it with the weak base that we know of, which is ammonia, and this will form I minus aqueous and NH4 plus aqueous. So in order to write the net ionic equation, we have to separate our aqueous ions and acids and such into their components, into what they look like in solution. So hydroiodic acid in solution automatically dissociates completely into H plus aqueous and I minus aqueous. And NH3 is a weak base. And in the video about electrolytes, we know that weak bases do not ionize completely. So therefore, NH3 will just stay NH3 aqueous. And then our products will, of course, be I minus aqueous, and ammonium just stays ammonium because it is a polyatomic ion. So on both sides, we see that the iodide is a spectator ion, so we can erase this and rewrite it as this. So as you can see, the H plus from HI will be donated to the ammonia in order to form ammonium, which has a plus charge because on the left-hand side we have a +1 charge, and on the right we have a +1. And also, if you're adding a +1 charge to something, then the resulting thing will also have a +1 charge. So that's an example of a neutralization reaction between a strong acid and a weak base. Now let's look at a neutralization reaction between a weak acid and a strong base. So a weak acid would be hydrofluoric acid, and we would combine it with a strong base such as sodium hydroxide aqueous, and we would get the fluoride anion, water, and sodium plus aqueous. Now let's try to figure out the net ionic equation for this and see where the acid-base reaction is actually happening. So we can't separate HF into H plus and F minus because remember, HF is not a strong acid, it is a weak acid, so it will not ionize completely into H plus and F minus. So therefore we will keep HF as just HF aqueous, and we had to add sodium hydroxide, so we have to separate that because it's a salt. And then we have the hydroxide, and our products will be F minus aqueous plus H2O liquid and sodium plus aqueous. So do you notice any spectator ions? Well, I sure do. The sodium is the same on both sides, so we can remove that, and I will rewrite it right now. So now that it's rewritten, we can clearly see that the H in HF is being transferred to the OH minus to combine to form H2O. And even though it's not really H plus, since it didn't ionize completely, we can pretend that the H in HF is an H plus. So once that happens, then, it gets transferred and it becomes water. And you're left over with an F minus because an HF, if separated into H plus and F minus, clearly shows that the F minus will be left over if the H plus is donated to the OH minus. But in our net ionic reaction or equation, we don't write HF separately because technically HF is kept together when it reacts with the OH minus. So this is the gist of how a weak acid strong base reaction works. So let me write weak acid and strong base. And now let's look at weak acid and weak base. So weak acid and weak base. So let me use another weak acid. Let's use acetic acid, CH3COOH, plus the weak base that we know, which is ammonia. And note that these are both aqueous. And let me see if you can figure out what the products are based on what we know about acid-base or neutralization reactions. What we know about them is that they happen when an H plus is transferred from an acid to the base. So in our case, acetic acid is our acid and ammonia is our base. So let's write the net ionic reaction first. So how do we write the net ionic reaction? Well, does CH3COOH separate into, acetate and H plus? Well, no, acetic acid does not ionize because it does not ionize completely in water since it is a weak acid, and therefore we keep it as, the acid form and not its ionized form, since not that much of it ionizes, so we don't write those, since the major thing is this and not its ionized form. So we will keep it as this. Now, what is the separated form of NH3? Well, NH3 does not ionize completely in water because it is a weak base, and because of that, we keep it as NH3. So look at that. We didn't have to rewrite anything because technically this over here is already our net ionic equation. Now let's figure out the products. So the H in acetic acid will be donated to the base, which is ammonia, and what we get as a result is CH3COO-, or the acetate anion in its aqueous form, of course, and we get NH4+. So notice how this lost an H+, so it became negative, and the NH3 gained an H+, so it became a plus charge. So if you lose an H+, you become more negative, and if you gain an H+, then you become more positive. So this is our net ionic equation because we couldn't separate anything into their components because weak acids and weak bases do not ionize at all. So I wanted to do a conclusion. So in summary, a net ionic equation will tell you the things that react, and it will exclude everything that does not react, aka the things such as spectator ions. So the net ionic equation shows you the action or the true reaction that's going on, and it excludes everything else that's not involved in the reaction. And note that salts that are dissolved can be written like this, or they can be written separated into their components like Ag+ and NO3-. But of course, that is up to you, and I tend to like to write it like this when it's in solution, since it's easier for me to identify the spectator ions by doing this. And for the same reason, HI aqueous or hydroiodic acid can be written as HI aqueous or as H+ and I-, and they're both aqueous. So note that there are many ways to do this, but this is how net ionic equations work, and this is an introduction to 3 more reactions in addition to the 3 that we covered in the previous video. Now you will cover all 3 of these reactions in more depth in the future, but this is just an overview and it's not meant to be comprehensive. So that's all for this video. I hope you learned a lot and have a nice day.